Welcome back to Part 3 of the recording on Multiarea OSPF. This presentation was developed by Lonnie Decker and Elaine Horn and will be presented by Elaine. When you finish the presentation, we strongly recommend that you look for the packet tracer activity, and there will also be a recording of a demonstration of the packet tracer activity. So please look for both files. In this part of the recording, we will be covering configuring multi-area OSPF version 2 and OSPF version 3. We will also cover verifying an OSPF version 2 and OSPF version 3 configuration, and conclude with reviewing some OSPF key points. So let's start with configuring multi-area OSPF. This is a sample configuration of multi-area OSPF version 2. In this example, router 1 is an area border router because it has two interfaces in area 1 and an interface in area 0. Router 2 is an internal backbone router because all of its interfaces are in area 0. Router 3 is an area border router because it has interfaces in area 2 and an interface in area 0. A router simply becomes an area border router when it has two network statements in different areas. And if you refer to the configuration, you will see that there's two network statements in two areas. Router 1 is assigned the router ID 1.1.1.1. This example enables OSPF on the two LAN interfaces in area 1. So here's the statements that are doing that. The serial interface is configured as part of OSPF area 0. So this is your serial interface. Because router 1 has interfaces connected to two different areas, it is an area border router. Please make a note that the method used for the wildcard mask, so if we look here at the network statement, is one method that you can use to configure the wildcard mask or the inverse mask. If you use 0.0.0.0, the wildcard mask does not need to be calculated. And you're going to notice that this address is the interface. So that address is this interface 10.1.1.1. Like OSPF version 2, implementing the multi-area OSPF version 3 topology is simple. There are no special commands required. A router simply becomes an area border router when it has two interfaces in different areas. So again, you're going to notice we've got two interfaces and two areas. Router 1 is assigned the router ID 1.1.1.1. You want to make note that even though this is IP version 6, this is an IP version 4 address. The example also enables OSPF on the LAN interface in area 1. So if you look at area 1, there's a gigabit 0/0. We have assigned that gigabit Ethernet 0/0 interface. Notice we put IPv6, OSPF 10. Don't forget that's your process ID. And we've assigned that to area 1. And the serial interface, when we look at it, it has been assigned to area 0. And again, because router 1 has interfaces connected in two different areas, it becomes an area border router. Summarization helps keep routing tables small. It involves consolidating multiple routes into a single advertisement, which can then be propagated into the backbone router area. Normally, Type 1 and Type 2 link state advertisements are generated inside each area. So in each area, you're going to have Type 1 and Type 2 LSAs. Those are going to be translated into Type 3 LSAs and sent to other areas. If Area 1 had 30 networks to advertise, then 30 Type 3 LSA summaries would be forwarded into the backbone. With route summarization, the area border router consolidates the 30 networks into 1 or 2 advertisements. So let's take a look at summarization in more detail. In the figure, Router 1 consolidates all of its network advertisements into one summary LSA. So it would take all the route advertisements in here and summarize them, instead of forwarding individual LSAs for each route in Area 1. Router 1 forwards a summary link state advertisement to the core router C1. So Router 1 will summarize them, send them on to C1. C1 in turn forwards the summary LSA to Router 2 and Router 3, and then forward it to their respective internal routers. Summarization also helps increase the network stability because it reduces unnecessary LSA flooding. This directly affects the amount of bandwidth, CPU, and memory resources consumed by the OSPF routing process. Without route summarization, every specific link state advertisement is propagated into the OSPF backbone and beyond, causing unnecessary network traffic and router overhead. The figure illustrates that summarizing networks into a single address and mask can be done in 3 steps. So in this particular example, we will be summarizing 10.1.1.0/24 and 10.1.2.0/24. Step 1, list the networks in binary format, which has been done here, and 10.1.2.0 was done here. So they're listed in binary format. Step 2, count the number of far left matching bits to determine the mask for the summary route. As highlighted, the first 22 far left matching bits match. So if we start looking at matching bits, the matching bits would stop right here. Right here, they are different. This results in the prefix /22. So you'll see the prefix down here, /22, and the subnet mask of 255.255.252.0. So this last line was showing the subnet mask, the calculation of the subnet mask. Copy the matching bits. So step 3, we're going to copy the matching bits. So we're going to copy all the matching bits up here. And then add 0 bits to determine the summarized network address. So we've got 0 bits here. In this example, the matching bits with 0 at the end result in a network address of 10.1.0.0/22. This summary address actually summarizes 4 networks: 10.1.0.0/24, 10.1.1.0/24, and 10.1.2.0/24 and 10.1.3.0/24. So in the example, if we are to summarize, and this would be our summary, and we came up with that with 3 different steps, you would be matching 4 networks, even though only 2 networks exist. If we were going to take that summary address and then put it into a configuration, this would be the correct way to configure that. So this configuration summarizes the 2 internal Area 1 routes, 10.1.0.0/24 up to 10.1.3.0/24 into one OSPF summary route on router 1. So take a look at router 1. When we put this configuration in, if we then do a show IP route OSPF, this is what you will see in the routing table of router 1. Notice how this entry has appeared with a null 0 interface. The Cisco IOS automatically creates a bogus summary route to the null 0 interface when manual summarization is configured to prevent routing loops. A packet sent to a null interface is dropped. For example, assume router 1 received a packet destined for 10.1.0.10. Although it would match the router 1 summary route, router 1 does not have a valid route in Area 1. So if we look for 10.1.0.10, we don't see it in here. We don't see a match to that. Therefore, router 1 would refer to the routing table for the next longest match, which would be the null 0 entry. The packet would get forwarded to the null 0 interface and dropped. This prevents the router from forwarding the packet to a default route and possibly creating a routing loop. Now don't forget, this will be advertised to the other routers. So let's take a look at updated router 3 routing table. Notice how there is now only one inter-area entry going into the summary route 10.1.0.0/22. So notice it's coming in as a summary route. That's the reason it has the O_IA in front of it. It's an inter-area route. And by doing this, you should be able to reduce the size of the routing tables in router 3. If you did not do this, so if we do not summarize in this particular network, instead of having one route in here, you would have 2 of them that were marked summary routes. And don't forget, those are type 3. We thought we would include a couple of extra summary exercises so that you can practice during this presentation. So if you want to stop the recording and kind of go back and practice, you can. So in this particular example, routing table B has all of these routes. And what we would like to do is summarize the first part of this and then summarize the second portion. So we're going to take all of these routes, summarize them, and end up, router B would summarize and send them on to Area 0 with 2 statements. So 2 summary routes would be sent, or 2 type 3s. So feel free to practice that exercise and see if you can get those to summarize. So again, the top portion here should summarize as 172.16.8.0 with a subnet mask of 255.255.248. And the bottom four should summarize to this. And just kind of test that and see if using the method that we showed you before, that you can get that to work out. In this example, we've also included the commands to summarize. So if you look at router 1, it is an area border router. It has area 0 routes from 96 up to 127. So it's got 96 up to 127, and notice these are /24. It also has in area 1, it has 32 up to 63. So if those were summarized correctly, they would look like this, and this is the network statements that you would need to put in. So those are your two network statements. So again, you've taken many routes here in area 0 and summarized them as one, and this will be sent, this one right here will be sent to router 2 in a type 3. This one will be sent to router 2 in a type 3. So notice how many routing entries we have saved. And again, that's a good one for practice. Now you're going to notice the syntax for configuring a type 5 summary from an autonomous system boundary router. So this is coming from some other type of autonomous system, is a little different. So if we compare, just make a backup for just a second, area 0 range, area 1 range, here it's summary-address. In this example, the external RIP version 2, 172.16.32.0/24 to 172.16.63.0/24 is summarized as 172.16.32.0, and this is a /27. And again, notice that syntax is a little different. Now, the configuration shown does not include advertising the routes from RIP into OSPF. The command to do this would be redistribute RIP subnets in the OSPF configuration. So we would need to add that statement here. And just as a side note, the default metric when redistributing into OSPF is a cost of 20. Now let's say that you had a default route that you wanted to share in an OSPF routing domain. To generate a default external route into an OSPF routing domain, you use the command default-information originate command in router configuration mode. So let's look at another sample. In this slide, you will see a sample configuration with a default route pointing to either ISP-A or ISP-B, and the default information originate command. So you're going to notice when you look at this down here, you've got an IP route, a default route, pointing in router 1 to 198.1.1.1. And in router 2, it's pointing to 198.2.1.1. So that's your default route. Now, if you want to share that, so router 1 and router 2 have this information. If they want to share that with the rest of the OSPF domain, you will have to put in the command default-information originate. The metric 10 or metric 100, that is an optional piece of that. That can be added if you wish. Now notice that again, in this particular configuration example, that one of the options for the wildcard mask in the network statement is simply 0.0.0.0. So entering the network 10.1.1.1 0.0.0.0 area 0 on router 1 tells the router to enable the interface for the routing process. As a result, the OSPF version 2 process will advertise the network that is on this interface. So it'll actually look at the interface and advertise that network. Of course, the advantage of specifying the interface is that the wildcard mask calculation is not necessary. OSPF version 2 uses the interface address and subnet mask to determine the network to advertise. As you study for the CCNA, make sure you know both wildcard methods, and we will review those later in the presentation on the OSPF key points. The next part of the presentation is on verifying an OSPF version 2 and OSPF version 3 configuration. So our key commands for verification should look familiar. You've used these commands before when you were doing single area OSPF. And don't forget, if you're running OSPF version 3, simply substitute IP with IPv6. So anywhere you see IP, just put IPv6. So let's take a look at a couple of them. We're not going to look at all of them, but we're going to take a look at some of them. Use the show IP protocols command to verify the OSPF status. The output of the command reveals which routing protocols are configured on a router. It also includes routing protocol specifics, such as router ID, number of areas in the routing process, and the networks including with the routing protocol configuration. So if you're going to notice, here's our networks, here's our number of areas, and here's the router ID. And again, notice it's going to show 2 areas here. So if it's showing 2 areas, that means that this is an area border router. Use the show IP OSPF interface brief command to display concise OSPF information of OSPF-enabled interfaces. This command reveals useful information, such as the OSPF process ID that the interface is assigned to, the area that the interfaces are in, and the cost of the interface. So a common command used to verify a multi-area OSPF configuration is the show IP route command. Add the OSPF parameter to display only OSPF-related information. This figure displays the routing table of router 1. Notice how the OIA entries in the routing table identify networks learned from other areas. O represents OSPF intra-area routes, and IA represents inter-area, which means that the route originated from another area. in just a little bit of review, the 110/1295 entry in the routing table represents the administrative distance that is assigned to OSPF, which is 110, and the total cost of the route, which is $1,295. The Show IP OSPF database command is another useful command for verification. It is used to verify the OSPF link state database. And in this one, again, notice we're seeing two areas, which means this is an area border router. And in addition, you can tell that each one of these routers have been assigned a router ID, because notice how simple they are. So over here, we see network addresses, we see some link IDs, but over here in this advertising router, we see the router IDs. Okay, let's review some OSPF key points. As we have tried to demonstrate, multi-area OSPF is a better choice for larger networks than single-area OSPF. It's going to solve the issues of large routing tables, large link state databases, and frequent SPF or shortest path first algorithm calculations. Your main area is going to be called the backbone area, which will also be called area 0. Recalculating the database is kept within an area. There'll be 4 different types of OSPF routers: internal routers, which have all their interfaces in one area; a backbone router; an area border router, which connects to area 0, but also has an interface in another area; an autonomous system boundary router, which has an interface in the OSPF domain, but also has an interface in another autonomous system, such as EIGRP or RIP version 2. A router simply becomes an area border router when it has 2 network statements. So if you look at the configuration and in IP version 4, if you see 2 network statements and they're in different areas, then it's an area border router. Link state advertisements are the building blocks of OSPF. Don't forget, all of these are a type of link state update, or a type 4 link state update. So there's type 1 LSAs. Those are your router link entries. All routers send these to the networks, to their neighboring routers. And don't forget, they're confined to the area. Type 2 LSAs are referred to as the network link entries and are flooded by a designated router. So you will only see these in multi-access networks. Type 3 LSAs are referred to as the summary link entries and are created and propagated by area border routers. So don't forget, the area border router will collect the type 1s and the type 2s and share those with other areas as a type 3. A type 4 summary LSA is generated by an area border router only when an autonomous system boundary router exists within an area. So if an area border router sees that there's an autonomous system boundary router in its area, it will send a type 4 summary link state advertisement. Type 5 external LSAs describe routes to networks outside the OSPF autonomous system. These are actually originated by the autonomous system boundary router and are flooded to the entire autonomous system. So they're flooded to the entire OSPF domain. The shortest path first tree is used to determine the best paths. OSPF routes in an IP version 4 or IP version 6 routing table are identified using the following descriptors. O, which are intra areas. O space IA for IP version 4 for summary routes, and just OI for IP version 6. And then the external routes will be either OE1 or OE2. And most of what we see in this course will be OE2s. Here's a sample configuration of OSPF version 2. I did not include in the summary the configuration of IP version 6 or OSPF version 3, so you should go back and review that as well. Notice in this configuration, though, that I did use both wildcard methods. So here you've got one where it's been calculated, and it's the inverse of the subnet mask. This is the network. These are in area 1. And this one, we've used the interface with the 0.0.0.0. What can make OSPF a little tricky is that it does not perform auto-summarization, but you can manually configure it using the area X range command, and the X will be like area 1 or area 0, and then range, and then behind that you would put your summary range. Or the other command, if you're doing external routes, is summary-address. These are the commands that are used to verify OSPF configuration. And don't forget, if you want to verify OSPF version 3, which is IP version 6, you would put IPv6 where you see the IP. Lonnie Decker has created a packet tracer activity so you can type the commands in and try all the show commands out. The packet tracer activity is similar to this topology. This is the topology. So make sure you take a look at it. And then also, he has provided a demonstration of the packet tracer activity in a recording. So make sure you find the packet tracer activity and the recording that demonstrates the packet tracer activity. This concludes the presentation on multi-area OSPF. Thank you.